Hey Math Nines, and welcome to our next topic in Unit 7. Today we're going to be discussing topic 7.3, which is similar polygons. The last two lessons we've discussed what enlargements are and what reductions are. So as a start for today's lesson, going to kind of get you to kind of open up your mind a little bit and do a little brain teaser here. I've got three objects that are shown here on my I guess grid paper here. You've got the same objects here in the notes if you've got the notes up at home, and hopefully you do, because they're certainly easier to read than maybe sometimes some of the stuff that's going on the board. You can get a little bit more detail off of those. I've got objects A, I got object B, and I got object C. What I'd like you to tell me is which of those two objects are either an original and an enlargement, or an original and a reduction, depending on which way you're looking at the objects. You're going to be looking for objects that have similar dimensions, that are going to have similar scale factors all the way through them. So I'm going to get you to pause the video for 2 seconds, think about the answer, and then I'm going to let you know what that answer is right about now. The answer is actually A and B. A and B, you could either say that B is being enlarged to A, or you could say that A is being reduced to B, because if you look at the objects, all of their sides have basically the same scale factors. This object here is 2 across the top, and then 1 there, 4 there, 2 there, 4 there, 2 there, 2 there, 1 there, 2 there, 1 there, and 2 there, and 1 there, which pretty much means that if I'm going this way, the scale factor of this would be 50%, because I've got a half size object of the original. I've got the dimensions are cut in half. If I was going from this object to this object, my scale factor would be 200%. And the reason I knew that those were pretty much the enlargements and reductions is because their dimensions are the same. They are what we call similar objects. This object here, object C, is kind of not quite a full enlargement, not quite full reduction. This side here looks like it's the stubby side over here, but it's twice as thick. It's pretty much like they took this object and then just basically cut it short about to there, and then this little part here is sort of removed. So regardless if it's this object or if it's this object is not proportional to either of the other two objects. So this object is clearly not an object that is relatable directly to objects A or B. So A and B are in fact reductions and or enlargements of each other, depending on which way you're looking, because they have the same corresponding sides. If their corresponding sides are similar to one another, which they are, they also have similar corresponding angles. All the angles in this case are 90 degrees, so they're all going to be correspondingly the same. 90 degrees here, 90 degrees there, 90 degrees there, 90 degrees there, 90 degrees there, 240 degrees on that corner there. So we know that all the angles are the same as well. These are what we would call two similar objects. And to indicate the two objects are similar, we're going to use this symbol here, right here in the middle. We're going to use that little squiggly line. So we are going to say that A is similar to object B. In this case, we use that little side squiggly line to indicate that that's in fact what we are representing there. So again, so we've already talked with reductions and enlargements. We've already discussed what similar objects are. We just didn't give them a name. Again, so similar objects are going to be any objects that have all their corresponding sides are similar to one another, as well as their corresponding angles. Now, because so far we've only been dealing with rectangles that have 90-degree angles, or in this case we had a 240-degree angle today, that's not a big deal for the angles. But we're going to start talking today about polygons. Tomorrow we'll be discussing triangles, which obviously have a lot of other angles other than 90-degree angles. So those angles do have to match. So I want to give you an example of kind of what that's going to look like right off the get-go. On your second page of the notes right over here, and I've got it written on the board, I've essentially got, a quadrilateral. It's like a four-sided polygon. It's not really a square. It's not really a rectangle, because its angles are not a 90-degree angle. So we can't really call it a rhombus. We can't really call it a parallelogram, because they don't have matching sides that are at the same angle. So these are just basically quadrilaterals, or a form of a four-sided polygon. So in this case, I want to determine whether or not these two objects are similar to one another. Like, do they have the same corresponding sides. Are the corresponding sides similar to one another? Are the angles of the corresponding angles, are they corresponding to one another? So how do I do that? Well, what I'm going to do in this case is I'm going to assume that we're dealing with a reduction. I'm going to say that this larger polygon, which is, by the way, polygon PQRS, so we call that polygon PQRS right down there, is it similar to, and I'm using the same letters in the same positions to indicate the corresponding sides that look the same, that have the same angles. Right now they're drawn the same, so that makes it very easy. Later in the unit, we're going to start flipping objects around, which makes it a little bit trickier to identify the corresponding sides. But I have PQRS, which is that similar to object ABCD. So what I'm going to do is I'm going to look at my corresponding side. So the first corresponding side that I see is I've got 1.5 corresponds apparently to 2.1. Because this is a reduction, I'm using this as a reduction, I'm going to basically use my scale factor equation, which is my scale length divided by my original length of the original, which is 1.5 divided by 2.1. Now, be aware, in my notes, I'm doing this as a reduction. Could you do this as an enlargement and just flip the numbers around, and would you get similar? You get different numbers, but the process is still going to be very much the same. What you're looking for on all four sides of the object is you're looking for matching scale factors. If you can calculate that all the scale factors for each corresponding side are identical to one another, you've got essentially winner, winner, chicken dinner. You've got two similar objects. If I find that the scale factor on one side does not match the scale factor of another side of the object, then I do not have similar objects. They might be close to one another in shape, but they're not identical. So they're not classified as similar objects that you're basically scaling up or scaling down. So what does that mean? Well, I just said that AB is 1.5, PQ is 2.1. When I divide that, I'm going to get a scale factor of 0.71 or 71%. If I now do the remaining sides, if I take 3 and divide it by 4.2, if I take 3 and divide it by 4.2, if I take 2 and divide it by 2.8 to represent each of the scales on each of the corresponding sides, what I'm going to discover is every single one of those is going to equal 0.71, which is good. If we're trying to calculate that this object is similar to another, that's exactly what we want to see. If the scale factors, again, didn't match, we got a problem. But because all the scale factors on all four sides, and again, you can look at the notes, all the calculations are here in my note package if you want to take a look at it at home up close so you can kind of see the math that I did specifically. You're going to find out that all the scale factors on all four sides of these objects are the same to one another. That means that I can clearly say that ABC is in fact similar to PQRS. As a side note, I also want to tell you about the angles of this object. We didn't have to calculate any angles because we were calculating the sides in this one. This angle here, which would be angle PQR or RQP, because the angle is bound off that Q point. So we basically say the angle is the middle letter. So in this case, if I wanted to write this down, let me give myself a little bit of board space here to write this down. I'm going to actually move that on the board so you can actually see this. So I wanted to compare my angle. So I'm going to say that angle PQR, and by the way, angle I would just write down as a little angle like that. It's not a less than symbol. It's a little different than a less than symbol. It actually looks like this. It's more of a straight line. The angle symbol is a little different than the greater than. It would be the less than symbol in this case. If I wanted to say that these angles, actually in this case, they're not going to be similar. The angles are actually going to be equal to one another. So the angle PQR is going to be equal to angle ABC. So because of that, and because all the other angles, as you can see, are indicated by special colors and notations, as they are on the diagram, all the corresponding angles of these two quadrilaterals are the same, which is another good sign to indicate that they are similar. If I had objects where the angles were different, that would indicate that my corresponding sides have different lengths in relation to one another that are not proportional, which means that the angles are going to change as a result. So You can check the validity if two objects are similar by either checking their angles in each corner to make sure that they're all the same, or you can measure the scale factors and whether those scale factors between each of the corresponding sides of the two objects are consistent throughout the entire object. So hopefully that makes some sense, and if it doesn't, I would recommend you take a peek at the notes, and I will have a kind of a refresher video for you at the end in case you need a little bit of extra practice or a little bit of extra information on that. All right, it's your turn now. Now that you've seen how I calculated that previous quadrilateral, I got three rectangles here that have various dimensions. I've got rectangle ABCD, which has the dimensions length 8.5, width 2.5. I've got the next rectangle, which is rectangle EFGH, which has a length of 8.4 and a width of 2.4. And I've got the final rectangle, which is rectangle, in this case, I could say it's going to be JKMN, which is going to have a length of 5.25 centimeters and a width of 1.5 centimeters. So what I want you to figure out is two of these rectangles out of the three are similar to one another. I want you to figure out which two of these rectangles are the ones that are similar to one another. Which ones, in fact, have the same scale factor on each of their corresponding sides. So if you feel like you can answer it, pause the video right now, do some calculations. I'm going to quickly show you how to do it here in a couple seconds right about now. So here's how I'm going to do this. What I'm going to do is this. I'm going to first calculate the relationship between rectangle ABCD and EFGH, and what I'm going to do is I'm going to scale it up. So I'm going to pretend that EFGH is being scaled up to rectangle ABCD. So what I'm going to do is I'm going to calculate my scale factors on each side. So it's going to be 8.5 was my scale factor on that length. The original is going to be 8.4, and my scale factor for my width is going to be 2.5, and I'm going to divide that by 2.4. Well, when I do this, I'm going to get two slightly different numbers. They are slightly different, but they are different nonetheless. My scale factor for my length is only 101%, and the scale factor for my width is 104. Because they don't match, I clearly know that these two rectangles are not similar to one another, so I can eliminate that as a possible right answer. The next ones that I'm going to look at is I'm going to look at ABCD, and I'm going to compare it to JKMN. I'm going to compare it to that one. And I'm going to do this as if I was doing a reduction. So it's going to be this one being reduced down to this rectangle here. So I'm going to basically use my scaled length, which is 2.5, divided by 8.5, which is the original length of the original rectangle. And I'm going to take 1.5, and I'm going to divide it by the original width, which is 2.5. When I do that, I am going to get, again, slightly different numbers. I got to get a calculator out. In my notes, by the way, I did it the other way. I went from this one to that one to enlarge it. I could have actually done that here. In fact, let me just do that just to kind of be consistent with the notes. So what I did with the notes, and again, can you do this either way? Yeah, you can. I'm just trying to keep this consistent so that you can see what I'm doing in my notes is consistent with what I'm doing on the board. So in this case, I'm going to just reverse that. I'm going to assume that we are enlarging from 5.2 to 8.5, and we are enlarging from 1.5 to 2.5. So when I do that, again, I could have done it either way. I could have reduced it or enlarged it. It's still going to give me either the two same answers or two different answers. In this case, I'm going to wind up with numbers that look like this. This is going to reduce down to, this is going to give me a scale factor of 162%. This one's going to give me a scale factor of 167. So again, I do not have matching scale factors on the sides of these rectangles. That indicates that they're not similar. So by process of elimination, we pretty much now know that I think it's going to be JKMN is going to be similar to EFGH, but let's just check the math to make sure that we haven't been doing something egregiously wrong. So what I'm going to do here is I am going to basically do I'm going to do an enlargement again. So we're going to assume that we're enlarging from this rectangle to that rectangle. So we're going to use our scale factor equation again, which is going to be 8.4, which is our scale length, divided by our original length, which is 5.25. I'm going to also do the scale factor for my width, which is 2.4 divided by 1.5. And now in this case, when I punch these numbers in, guess what? Lo and behold, the numbers actually are equal to one another. I get 1.6 for both of them. So the scale factor for both my width and my length is going to be 160%, which is great. That means that we know that rectangle EFGH is similar to rectangle JKMN. So I can basically figure that out. And all I needed to do to figure that one out was basically compare my scale factors for each of the sides to make sure that I had two matching scale factors. The scale factor for my length of my rectangle should match the scale factor of the width of my rectangle. And the only time that occurred was when I compared rectangle EFGH to rectangle JKMN. So that's how you figure out that one, folks. On the bottom here, I've got a polygon that's been drawn. It's actually a pentagon, five-sided object. I've got the tops of this sucker, which are 2.8 and 2.8. I got a right angle at the top. I've got two angles here that are 135-degree angles each. I've got a side of 2 centimeters and 2 centimeters, and across the bottom I have 4. Now, this is probably going to be easier for you to do if you have some graph paper. And I mentioned to you before this unit, graph paper is probably a really good thing to have. If you're going to practice this question right now, I would definitely recommend you've got some graph paper on you to try this out. And I would just recommend that every grid in the graph paper is basically going to be equal to 1 centimeter. So each little box in the grid, make it equivalent to 1 centimeter squared. And that way you can draw this out. So in this case, if I was drawing this out on a piece of grid, it would be basically 4 rectangles. It would be 4 rectangles wide by, 4 boxes wide by 4 boxes. So what I'm going to do now is I'm going to draw myself a little bit of grid paper here, just so I can do this. What I want you to do is I want you to draw a scaled up or a scaled down version of that polygon. You can make it bigger, you can make it smaller. You can set the scale factor that you want to use. There's no right or wrong way to do this. I'm going to show you, I'm going to do an example where I'm going to enlarge this by a scale factor of 200%. So if you want to try that to see how your answer compares to mine, you certainly can, but you're not obligated to have to do a 200% enlargement. You can do a 50% reduction if you wanted to make it even smaller. But I'm going to do one that is going to enlarge it by 200%. So I just got to make sure I have enough boxes here to do this properly. And I don't really have enough. So I'm going to have to make a couple more. I'm going to have to make my boxes smaller to make this work. So you can kind of work at your own pace, and then I'm going to work at mine. You can see the high-tech precision nature of my grids that I'm doing. Terribly precise. But when you're doing guerrilla style teaching from your basement, what else can you expect? Hopefully that was enough time to kill. You can pause me if you still need a little bit more time. Here's how this is going to work. So I know I'm going to enlarge this by a scale factor of 200. So I'm going to start off with the bottom. I know that it is a 4 centimeter bottom. So I'm going to basically count off. Remember I said each of my boxes in the grid paper I'm going to make equivalent to 1 centimeter. So I'm going to go I'm going to start here in this corner. 1, 2, 3, 4, 5, 6, 7, 8. There's the bottom of my polygon. The sides are 2 centimeters up, which means that I need to make them now 4 centimeters up because I'm enlarging by a scale factor of 200. So 1, 2, 3, 4. There's that. And 1, 2, 3, 4. That gives me my sides of my polygon. Now I've got to worry about the very top. This point, I don't have one, but I would really recommend you've got like a compass. If you have a compass, what you would do now is you would essentially measure an angle that's 135 degrees on the compass. what I'm going to do is I'm going to find my middle point. So I know the top of my polygon is going to go somewhere along that line. I know the polygon is going to go along that line. Now, if I had my compass, I would lay my compass down and I would basically angle off 135 degrees. I would make a little tick mark, and then I would basically draw my line straight to wherever it intersects that line. Now, I obviously have not measured that angle, but you get an idea of how I would do it. You would want to make sure that this angle here and that angle there are both, again, the same angles. They need to be 135 degrees each, and you're only going to figure that out by using a compass. I don't have a compass on me. I didn't actually have one. I didn't think about grabbing one for this lesson today, so I do apologize for that. But using a compass would be the way to formalize basically where the top of that polygon is. And I think I did a pretty good job, because when I look at that angle there, that looks close to 90%. So that's a pretty good estimation. It's probably not exactly right, but it's pretty darn close. Now, you'll notice that this object is much larger. Obviously, my scale factor here, I'm using grid paper. Now, if you would have actually done this by the letter, you would have had an object that was 4 centimeters. You would have actually gotten a ruler, measured out 8 centimeters, and then 4 centimeters and 4 centimeters. Use your compass to basically plot the top of the gable. Where the two lines meet becomes the top of the Pentagon, and away you go. So that just basically shows you how to draw a scaled up diagram for essentially, in this case, two similar pentagons. All right, a couple more, and then we're done for today. A couple more questions for you. Give you a couple here. So now that we understand what similar objects are, and we understand that similar objects always have the same scale factor on all their corresponding sides, this allows us to run equations where we can figure out missing sides. So in this case, we're given essentially two objects, and we are, even though they're probably not drawn to scale, because they're not, you see my little symbol in between here, this indicates that they are similar to one another. So I know that if I understand the scale factor on one of the corresponding sides, if I can calculate that on one side, I can use that corresponding scale factor to essentially find out missing sides on either one of the object, how long they are. So in this case, we're looking at two things that we're trying to figure out. We're trying to figure out the length of GH, which would be that side right there. We're trying to find out that missing side. And we're also trying to figure out the length of NP, which is that side right there. So I'm going to do GH first. And if you want to do this before I even discuss it, pause me right now. If you want to see how to do one before you do the second one on your own, go right ahead. But you can pause me right now. But here's how you do it. The key to the question right now is this side over here. IJ and AB, we've got dimensions for both of them. And that's what we need to answer one of these questions. There needs to be at least one side where we're given the dimensions of both of them so we can calculate out the scale factor. Now, I can scale factor this up, or I could scale factor this one down. I'm going to basically, I'm going to scale it down. So I'm going to say that this is a scaled down version. So I'm going to assume that we're actually making this one smaller. So what I'm going to do is I'm going to calculate 5.4 over 8.1. Because I know that's my scale factor. And I know that scale factor has to be consistent all the way through the object in order for them to be classified as similar. So now I'm looking at my missing side, which is GH. Do I know what the corresponding length is on the other object? Well, in fact, I do. They've given me that length right there is 32.4. So what I'm going to do is this. The 8.1 corresponds to my larger object. So I'm going to put the 32.4 as my denominator for that one, because this would be the original size before I shrank it down to this object over here. So the missing object now is essentially GH. So by doing this, I'm setting up essentially a cross multiplication scenario. I'm basically telling that I know the ratio of AB to IJ is going to be the same as the ratio is for GH as it is to PQ. I'm given 3 of the measurements. The only measurement I don't have is that measurement for GH, which is what I'm going to solve by basically doing a cross multiplication scenario. I'm going to take 32.4, multiply it by 5.4. I'm going to divide by 8.1, and that's going to give me a GH value of 21.6 meters. Now, logistically, this makes sense because we know that if I divided 5.4 by 8, it's going to give me a scale factor, I think it's going to be somewhere in the high 60s. If I took 21.6 and divided by 3.2, I'm going to get a value that's around in the high 60s as well. So the scale factors look like they line up. If this number got bigger, then there's obviously a problem. How can this number be bigger if the number on the other one is smaller? It's sort of common sense, right? So in this case, GH is going to equal 21.6. That's how I calculate that one. Pause me now if you get that now. Try to see if you can do the same thing for NP, because you're given essentially the same. By the way, the start's going to be the same. You're going to use this 5.4 over 8.1 to start this whole process going. See if you can line up the ratios the way you need them to calculate the missing length for NP. Pause me if you need to, and here comes the answer right now. I'm going to still use my ratio of 5.4 over 8.1 because, again, I know those sides are corresponding sides, and the ratio, their scale factor, is going to be the same as the scale factor for all the other sides. NP I'm missing, which is corresponding to this object now. So my NP is going to correspond under the denominator now because it's part of the object that has the 8.1 value, right? So it's got to be part of my denominator. Luckily, I do know my value of its corresponding side of the smaller object, which is 27.0. So I'm going to put down 27.0 there, and then I'm just going to cross multiply. 27 multiplied by 8.1 divided by 5.4, and that's going to give me a value of NP as being 40.5 meters. And again, it makes sense. We know that this object here is 27 meters. We know this is the smaller object based on the fact that this dimension is smaller than that dimension. So this here should be a larger dimension. And that's how we calculate it. There's a lot of cross multiplication in this unit. So if you're good with cross multiplication, this is going to be something that you're going to be probably very happy to see in this unit. If you're not good with cross multiplication, then you maybe need to come and see me to get some extra help on how you do cross multiplication effectively. But it's certainly a really powerful tool in Unit 7 to know cross multiplication for sure. Got one more question before I sign your homework for the day. What I've got here is a question on this page of the notes. I'm going to read it to you. A rectangular door has a height of 200 centimeters and a width of 75 centimeters right there. And it's similar to a door in a dollhouse that has a height of 25 centimeters. Based on this information, I want you to calculate the width of the dollhouse door. So we're basically being given 3 bits of information again. We've got 2 height values, and we've got 1 width value with a missing width value. This is pretty much the same methodology that we did up here. Give it if you want to try it right now. Pause me right now. Give it a shot. If you need to see me watch me do this one more time, I will show you one more time in about 3, 2, 1. Here's how we're going to do it. I've got my original object. I'm going to scale this sucker. Now let's scale it. Let's scale it up. Now, you know what? There's even a better way to do it than this. Here's what I'm going to do. I know that the dimensions on my door, on my main door, are 75 by 200. I know that. There's another way you can do it, by the way. 75 over 200. I want to calculate the width of my dollhouse, which in theory, the ratio of my width to height on both doors should be the same. If they're similar, the ratio between the height and the width should be the same between the both of them, right? So what I'm going to do is I've been given the height of my dollhouse. So my height corresponds to the 200 value. I still don't know my X value though. So basically what we're saying is the 200 of the dollhouse, 200 centimeters, gets reduced down to 25. What's my 75 getting reduced down to on the dollhouse? So I'm just setting up again another cross multiplication scenario to see what happens. Well, what you're going to do is you're going to take 75, multiply by 25, you're going to divide by 200. That's going to give you a value of X of roughly 9.4 centimeters. And again, How can I verify the answer? Well, if I took 75 divided by 200, and I haven't got a calculator on me right now. I do, it's over there, but I don't want to grab it. Do this at home right now. Take 75 divided by 200. You're going to get a value. You're going to get a decimal number. This number I know is going to be less than 0.5. It's going to be probably around 0.3. I'm going to say about 0.3875 ballpark. I'm probably off by a little bit, but it's under 0.4 as a decimal value. I'm willing to bet you a ton of money. And you can call me on this when you get to class the next day or whatever. You let me know, you send me an email or whatever. If I take 9.4 and divide it by 25, I got a prediction. That number is going to be the same as when I divide 75 by 200. I guarantee you. And I know that number is somewhere between 0.37 and 0.4. I know it's less than 0.4. But if you plug that into a calculator, this ratio, you take 75 divided by 200, is going to be the same answer as if I divide 9.4 by 25. Again, that's the power of the ratio, the power of the cross multiplication. We're dealing with objects that have similar ratios because they are in fact similar. That's the whole idea behind similar objects. Ladies and gentlemen, that is your 7.3 notes. Thanks for tuning in. Before you head out, if you have any more questions or you want to give it another whirl, maybe you want to hear someone else's opinion on the matter, give this video a watch up here. That'll maybe help you out if you're still having some issues with calculating sides of corresponding sides of similar objects. The homework for tonight, you're going to complete practice questions 4, 5, 6, 9, 10A, 11, and 16 on pages 341 and 342 in your Math Makes Sense 9 textbook. That is it for today. Won't you join me next time? If polygons weren't great enough for you, let's simplify it a little bit. Let's maybe reduce the sides of our objects next time. Next time I'm talking to you about similar triangles. Have yourselves a great day, and we'll see you next time right here on Science According to Mr. B.